Welcome to the 2021 Crop Management Conference session. Today we're going to do something that is a little bit different for me and probably for you as well. We're going to talk a little bit about climate change and what effect climate change might have on crop yields in Illinois. Now, I guess at the start, I'd have to say that it's not a topic I ever expected to talk about. We've been hearing about climate change for quite a while. Some people have been very skeptical about it. Some people still are very skeptical about it. And we're not going to spend a lot of time, in trying to convince people that the climate is changing, but the evidence is pretty clear that it is. And we're going to talk about why. And most importantly, for our purposes today, we're going to talk about what effect this might have on crop yields in Illinois. And that's the one that really gets me interested in it, because as we look forward, I've seen real tales of woe about how our crop yields are going to take a nosedive. And basically, if you believe some people, pretty good chance we'd be out of business producing the crops in Illinois that we produce if the climate changes as expected over the next 50 to 75 years. And I can say at the beginning, we're not going to come to that conclusion. In fact, we're going to talk about how to look at things like that. And it's just kind of an interesting exercise. And we'll get started on that right now. So why this topic? Well, yields in Illinois, corn and soybean yields, have been trending steadily upward for more than 60 years. We want to consider, I guess, in general, how long this might continue. And we're not going to come to a solid conclusion today, but I am going to argue that, you don't just suddenly reverse that and have yields start to go down suddenly in a year or 5 years or 10 years. But the topic is here because as carbon dioxide in the air continues to rise, and along with that, global temperature is rising, we'll talk about that. We want to consider how that might affect weather and crop yields in Illinois as well over the next 50 years or so. And these topics are related from the standpoint that, there's some positive things with increasing carbon dioxide. There's certainly negative things with increases in temperature. And we want to see if we can sort out what that might mean. And here's what we'll do. We're going to use yields and weather over the last 40 years. So I sort of arbitrarily chose 1980 to 2019 to try to find out how weather affects yield. And we call this exercise generating a model that relates weather to yield on an annual basis. So that's a pretty straightforward procedure, and we'll talk about it. It's not one I've done a lot of, and not one that too many people are terribly interested in it, but it helps us understand, if we look over 40 years of data, we can see, does higher temperature during the summer mean higher yields or lower yields or somewhere in between? And what does rainfall do? And we can actually get numbers on that. And we'll use Illinois weather predictions made by climate scientists in these models of climate models. And we'll talk a little bit about that as well to estimate how the yields might change as the weather changes. Now, there's not real definite things in terms of how weather is going to change, but there's certainly been a lot of work done on this and some very high powered work in terms of trying to model these changes in weather that we might see. We're going to consider all of Illinois in this yield weather scenario, and we're also going to break it down into these three parts that I show here. And we're going to do this by crop reporting district. The lines I drew straight there aren't exactly the ones, but Northern Illinois is going to be crop reporting districts. The Northwest and Northeast are 1 and 2. Central Illinois districts 3, 4, and 5, which is west, central, and east. And southern Illinois is the other 4 crop reporting districts then. These were never really set up to do exercises like this. The soil-wise and yield-wise, you know, some of these are sort of in the wrong category, particularly counties over here in sort of the central Illinois, southwest of that, Sangamon and counties like that. They ended up in that west-southwest, which ends up in the southern Illinois in this regard. But we'll just use it because we have weather data from that, and we have yields from those, and so that's what we're going to do. So here's the gist of what's happened over the last 40 years. And in northern, central, and southern Illinois. And I have all of Illinois on here as well. So you can see there's a pretty good scatter in these. I left the data in from 2012, even though those were, you know, really low yields compared to trend line. But, you know, unless we can rule out that a 2012 is never going to happen again, I guess we have to include it. And these are the rates that I put on here. This is the rate of yield progression, sort of on an annual basis. So all of Illinois has gone up over the last 40 years by 2.2 bushels per acre per year. When you think about it, you know, times 40, that's 88 bushels per acre. And I started at Illinois in 1982, so I've been here pretty much all of this time, and it doesn't take much to remember when we thought 120 bushel average state yield was really pretty good. And you can see here in the early mid 80s, you know, that's about where we were. Northern Illinois and central Illinois have been a little bit faster than all of Illinois. And of course, southern Illinois is a little bit lower. So northern and central Illinois were up at about 2 1/3 bushels per acre per year, and southern Illinois just under 2 bushels per acre per year. So these are pretty hard numbers because they're from NASS, they're the reported official yields. I'll just mention that for at least so far as we know, for 2020, they're going to be fairly close to trend line. Statewide, we're supposed to be at 195, which is slightly above trend line. Then these are the soybean yields then, and soybeans have been going up pretty steadily as well. There's a little bit less variability around the trend lines than we saw with corn, but on a percentage basis, not too much different. But all of Illinois over that same period has gone up at 58 hundredths of a bushel per acre per year. And that's been fairly consistent across the regions. Northern a little bit lower than central, and southern right at the average, southern Illinois right at the average. Those yield levels are a little bit different from northern, central, and southern, as you can see, but the slope of those lines is pretty similar. In other words, we've made about the same progress everywhere. I did cheat a little bit on this. I dropped the 2003 yields. Some of you remember in 2003, it was a decent corn yield and a terrible soybean year. And, you know, I say that the weather pattern was very unusual. Again, that doesn't mean that we can never have that again, but to be honest, leaving 2003 in really messed things up. And, you know, it was sort of in the middle of the range there, and yields were about 10 bushel less than trend line. It was just worked a lot better for our purposes to say, well, we can't rule out that we'll never get that again, but it was a highly unusual year. And the ratio of corn to soybean yields that year was, as I recall, above 4, which is way out of line with anything that we had seen before that and anything we've seen since. I wanted to make a note about soybean yields. If you actually put a curve to them instead of a straight line, the curves fit a little bit better than the straight lines do. And people have noted this, over the last, since about 2014 or 2013 or 2014, the yields have been substantially higher than they were before that. And so the poly means a polynomial, you just put a squared term in, and these actually fit better. The problem, if you're looking over the long range, is when you put a squared term in like this, obviously by 20 years from now, they'd be 120 bushel. And so we're going to be a little conservative here, and we're going to use the straight lines. But I just wanted to make a note of this. We don't see this in corn, but we do in soybeans. And you can see out here at the right-hand side, these high yields out here that have brought us up there. So let's look at what our weather has been over these same 40 years. And this is part of this model building exercise that I talked about. Rainfall has actually increased a little bit, but it's really variable. And so, if you put statistics to it and say, was this a real increase? You'd say, well, maybe not. It's so variable that they don't give you a very good prediction for what rainfall is going to be, for example, in 2020 here by looking at those lines, because everything is so far off the line. And it's increased, though, over the last 40 years at about a half an inch per decade, highly variable, but that means that it's up about 2 inches over that period, the average summer rainfall. This is rainfall from June through August. And I did put these together and not try to do things by month, because by month gets, really messy. And we got pretty good models when we did it this way. And so I've just kept them for our purposes today. I will say that this is not going to be the last word on this, that I may tinker some more with these. The maximum daily, so these are daily maximum growing season temperature, and I just averaged them again over the 3-month period, June through August. And you can see that they've actually trended down a little bit over these last 40 years. Again, not a very strong trend because there's so much variability, but they were supposed to, the earth has certainly warmed some over this the last 40 years, as we'll see. But here in Illinois, it would show that at least the maximum daily temperatures have not risen over that period of time. The minimum daily temperatures have risen, or at least those lines move up at about 1/4 degree per decade, so about 1 degree Fahrenheit. That's actually not too far from the increase in the Earth's temperature over at least part of that period. So, but I don't want to make too big a thing out of that. You can see that it's also highly variable, but that one does show a different trend than maximum temperature. And that's this is one of the reasons that people have been thinking, well, that higher night temperature, that's got to be really hard on crops. And if that keeps going up like that, we're going to start to lose yield. So that's one of the reasons we're interested in doing this exercise. So this just sums up what the trends have been over the last 40 years in weather. The growing season rainfall has trended up. Temperature trends are pretty consistent among the regions, but at different levels. And there's about 2 degrees in temperature that separates southern and central Illinois, and about 2 degrees that separates central and northern Illinois. Maximum daily temperatures trended slightly downward, and minimum daily temperatures trended slightly upward, about 1 degree for each of those over the last 40 years. So the relative to the daytime temperature, the nights have increased by about 2 degrees. And the weather, of course, is highly variable. Summer rainfall ranged from about 15 inches, between 5 inches at the low and 20 inches at the maximum. So that's a huge range. And average temperatures ranged up and down by about 10 degrees. these wide ranges in weather actually help us make our models a little bit better. If the weather was the same every year, you would neither be able to make a weather model nor would you need to, because you'd absolutely know what the weather is going to be the next year. So here's how we make a model then. We use this 40 years of growing season weather and yield data by region to find out how well weather explains yields by year. As I said, we're going to use rainfall totals from June to August, minimum maximum temperatures averaged over June through August. So it's about as simple as we can get. We drop the weather data out of the model that doesn't explain much of the yield variability. And I'll show you a little bit about that, but it's a pretty simple procedure to do that. In early runs, we included things like planting date. So I had planting date and crop development for corn. Those didn't have a very consistent effect. They certainly didn't have an effect over consistent effect from one region to another. And what that means is they didn't improve the model very much. In other words, if you put planting date in, you didn't get a better description of yield for central Illinois than if you left it out. And so when that happens, we just leave them out. We want these models to be as simple as they can and still do a decent job of predicting yield. This leaves us with a model that describes or predicts yield for each year based on the weather yield relationship over all 40 years. And so this is how we go about that then. I'm just showing you the data as I would have it on a spreadsheet. And you can see the rainfall and then the maximum temperature. And I use temperature squared here. So I made a note over on the left here. We include squares of some of the data. That's the temperatures here, the maximum and the minimum, to see if the yield responses are straight lines or curves. And I'll mention that a little bit on, in a moment. But we can't assume that everything is a straight. The more rain, the higher yield, or the more temperature, the higher the temperature, the lower the yield. Sometimes there's a curved effect, curvilinear effect, meaning that if you get really high rainfall, maybe you lose yield. And that's why we included them. Now, it doesn't mean we left them in if they didn't show that they were helping. But we generally include everything to begin with and then take things out as they show they didn't help. So then we line up the data like this and run what's called a multiple regression. You can just do it in an Excel spreadsheet. By the way, the last column there is yield, as you can see. That would be, we'd call that one the independent variable or the dependent variable, and all these others are the independent variables. They're the ones that, were put in. And I left year in because it's important to know if year by itself, in other words, if there's a trend over years, and you can probably already guess from what I've said to you that there is a trend over years, and we'll see what that is. So here's the corn model for all of Illinois. And here's the regression statistics here for those with interest. And, the R square value here is 0.865. The closer to 1 that is, and 1 would be a maximum, the better these variables that we used explain the differences in yield over years. The coefficients that are down here then, the intercept is just one that puts us in the range of where we're supposed to be. So that one's just a number without too much meaning, except if we didn't have it, we'd have yields that are way out of whack. And then what got kept in this one is year, summer rainfall squared, and then the summer maximum temperature. That's the only variables that we kept out of those we started with. And when the p-values here are, those coefficients tell you how much one unit change in the variable changes yield. And this says that each year adds 1.95 bushel. You remember we said it was 2.2 for corn. This is only 1.95 because now the weather is having an effect as well. The summer rainfall and the rainfall squared, you can see those effects. So we get 13.6 inches or bushels of yield for each inch of rainfall, but the summer rain squared is negative, and so we subtract something from that, and we'll show you how that looks as a curve. And then summer maximum temperature is a negative number. That means that for every degree hotter the high temperature for the day is, we lose 4.5 bushels of yield. These p-values are just, the smaller they are, the better, and they explain, you know, how useful that that variable is to explaining that. So I threw out the ones that were generally we use 0.05, and I threw out the ones that were 0.05 or greater. And as you can guess, that was most of them in this case. So here's what we mean then by a model like this. So the model based on those coefficients I just showed you, this is our starting point here, that intercept. Then year times 1.95 is the year effect. Summer rain times 13.61 minus summer rain squared times 0.48. So 10 inches would give us 136 here, but it would subtract 100 times this, or 48 bushels here. Summer maximum temperature then times 4.45, we subtract that. The R squared value of 0.865 means that 86.5% of the variation in yield was explained by this model. What that means is, you know, that the numbers are sort of on both sides of the line here. So what I did in this figure on the right here is I lined up, and I just showed you the actual and the predicted numbers here. There's a column for each. And so the actual is the actual yield, and the predicted is when we went through this exercise for each one of those and based it on the year and the weather only. And you can see how they line up here. So, you know, on average, they're just right. And in particular, very few years are yields are right on the line here. But the good thing is they sort of vary above and below, you know, kind of evenly. And so we're, you know, it's hard to know whether you look at this and say, man, I could be off by, you know, 20 bushel here. And that's absolutely the case. I mean, you can look for examples here for some that are almost right on and some that are pretty far off. But this is the exercise that we do. Could we get a better model than this? We probably could, but every time you add variables, you know, you have the issue of messing something up as well. And so I just wanted to keep this one simple, and we just stopped with this for now and called it good enough, I guess I'll say. So here's the models by region, and each one of them pretty much used the same variables. So we had the same ones that I showed for the whole state are in each of the regional models here. And the coefficients are different, as you can expect. So we know that, you know, these are going to give different values depending on what predicted numbers are in the future. All of them have year in them, and Northern Illinois has 2.2, Central 2.17, Southern 1.76. Remember, the whole state was 1.95. So for every year we go forward, we add that amount on the assumption that that's sort of what's going to happen that year if the weather is exactly the average. Having the summer rain on the summer rain squared terms means that yield responds positively to rainfall up to a point. Then it declines as it gets above that. And we've all seen years when it's very wet and we get yields lowered by that. And this just puts that into action here. And those break points are the top point of the curve. And I've showed a curve here. Basically here we just fix temperature and then, and let rainfall, I did rainfall over from between 5 and 20 inches to graph this. And we can see a high point here somewhere around 14 inches. So Illinois is 14.2, Northern Illinois is 15, Central 14.1, and Southern Illinois 13.8. That means as we go above that, then the effective rainfall would actually turn a little bit negative and it would accelerate. But you can see here, it doesn't fall off the earth or anything. It just means that, if we get 20 inches of rainfall in June, July, and August combined, that's likely not to be a very positive effect on yield due to cloudiness and wet soils and some of these kinds of things that we know comes with lots of rain. We do the same thing for soybeans, and I'm just going to show you the models here, and then we'll get to what these predict here in a minute. But for all of Illinois, it was a pretty simple one. We just had summer rainfall, summer rainfall, and summer maximum temperature. So we didn't have a squared term there, meaning basically that the more rain, the better for soybeans. I guess if we want to look at it that way. Southern Illinois, Central Illinois, and Northern Illinois, they all had a different model. So this just means I went through the exercise each time and saw what stayed in when we ran these models. And so we have rainfall, or Central and Southern are almost the same, but parameters are different, or the coefficients are different. Summer rain in Central Illinois only adds about 3,700s for each additional inch, but summer maximum and summer minimum temperatures both have an effect. And they're pretty complicated, so I'm just going to tell you that that's what they are. And you can see the p-values are small, so they should stay in. But you see Southern Illinois and the Central are pretty similar in that regard and sort of had that same response. When we got to Northern Illinois, temperature actually dropped out. You can see our squared values here. For the whole state, it was 0.88. Southern is 0.86, Central is 0.91, and Northern is 0.83. So Northern Illinois, we could put the rainfall in, and rainfall squared, both of those were significant, so we left them in. And in Northern Illinois, the peak response to rain occurred at 16.3 inches. You might wonder how we get these things so precise. Well, the data aren't real precise, so take them with a grain of salt, but we can just use the coefficients and actually calculate these. And that's what I did in this case. What does having year in the model mean? I mean, that sounds sort of weird, but we could run these models without it, but they aren't going to fit very well because yields are increasing at a steady rate. That's what having year left in the model means, independently of the weather. Year also isn't just a calendar year. It includes crop genetic progress. And we think that's been really steady. And changes in management that contribute consistently to yield. So everything we do over the years, better seed treatments and this sort of thing, they all kind of add up into that year term. It'd be very complicated to separate those things out and say, okay, well, how much do genetic improvements actually add? My opinion is they add a lot because most of these other things show only modest effects. But that's why having year, and that's why I stopped to mention it here. It also includes things like increases in atmospheric carbon dioxide level, which is considered a positive, especially for crops like soybean. Carbon dioxide is the food source for plants. I mean, it's what builds the plant, the carbon from carbon dioxide, using the energy from the sun. Because crop breeding, and this is kind of an important point, because we do crop breeding under actual conditions. In other words, we don't build a big greenhouse and do all the breeding in there. Any changes that take place, things like carbon dioxide and temperature, sort of get bred into crops over time. This is one point that a lot of scientists haven't paid very much attention to, but I think it's really critical. If you had asked us, 40 years ago, are we going to have trendline yields of 200 bushel in Illinois? Back when 200 bushel yield in a field was a rarity, people would have said, "Oh, I just don't think that's going to happen." Well, it did, and so I give a lot of credit to this sort of thing, to the genetic improvements that have taken place, and we match our management to the genetics. But without that genetic potential, if we were growing, hybrids from the 1970s today, we would not be looking at the yield levels that we're at. What this means, though, is we're looking at things like climate change, the effect of raising the carbon dioxide level artificially. And that's what they do out here in Soyface. Those of you who have seen it here on South Farm, Soyface is, free air carbon exchange. So they increase the carbon dioxide by releasing it into the air. If we do that using the current varieties, and we have little choice, that's the only varieties we have, uh, it, we're not able to predict how these current, recently developed varieties are going to perform in 30 or 40 or 50 years once actual carbon dioxide levels get that high. So it's a kind of a subtle point, but it's an important one, and that is, until we have varieties developed for the year 2050, we're not really going to know how they do in the conditions of 2050. So it's a big unknown when it comes to that. Well, let's switch gears a little bit and talk about global warming and climate change. This is just a sketch from 1880, which is when they started having accurate temperature measurements, up to today. And you can see what the temperatures have done for the whole globe. And I want to emphasize that this is for the whole globe. So it's not for Illinois. This says that it's gone up using the period from about 1940 to 1980 as the baseline. It's gone up now by about 1 degree Celsius, which is about 1.8 degrees Fahrenheit. And yes, it has ups and downs, and we get a cold snap and people say, "Oh, look at that global warming isn't happening." Well, it doesn't happen the same everywhere, as I'll mention again, but certainly the trend is there, and it's pretty much inescapable. One thing there is no question about, and that is that carbon dioxide levels in the air are rising. Carbon dioxide is released by burning oil, coal, and gas, and it has no other place to go. It stays in the air. Some of it dissolved in the ocean. As the oceans warm up, that's amount that dissolves in them is actually a little bit less. Carbon dioxide and other gases in the air act as a greenhouse to trap heat from the sun in the Earth's atmosphere. So that's been rising since about 1970, as I showed you, and is about 1 degree Celsius higher than the baseline. This change is not distributed uniformly around the globe, and that's an important thing to keep in mind. Changing air temperatures have affected rainfall as well, but it's more of an indirect effect. It's not uniform. Rainfall in the Corn Belt is showing no real trend. And I'll return to this a little bit, but rainfall distribution patterns have changed in some regions of the world, though. And we expect that almost everywhere, the higher air temperatures, even modestly higher, are going to change sort of the distribution, and more large storm events and more extended dry periods is what people generally look at. Are you going to be able to tell that, say, in the next 5 years or 10 years? Well, probably not very well. I mean, many people, every time it rains a lot now, say, well, there's climate change for you. And it may be related to that. But certainly, these things don't happen all of a sudden, and then it's always a different pattern. Well, here, if you wanted proof, is the carbon dioxide. So the carbon dioxide level in parts per million is here. And they went back and looked at tree rings and so on to see what it might have been to, in 1750. But if we just pay attention, when I was first learned about carbon dioxide in crops, which was about 1970, we were talking about 325 or so parts per million. And today it's 415. Think about that. Just in, the last 50 years, it's gone up by that amount. And, this is one that there isn't any debate about. I mean, we can argue about what effect that has on weather, but we certainly can't argue that that carbon dioxide has not increased. And some people are even willing to argue that now. Here's the carbon dioxide emissions for the whole world. This is billions of tons per year. So you look at parts per million, you say, boy, that's not very much. 300 parts per million. Well, there's a lot of air. In fact, the atmospheric pressure at the Earth's surface is about 15 pounds per square inch. That's how much the air above that square inch weighs. So all the way to the top of the air, a square inch weighs about 15 pounds. And if you multiply that times by 144 square inches per square foot, and then 43,560 square feet per acre, you pretty much soon see how much air there is in the world. But so putting in 30 or 35 billion tons of carbon dioxide, you can see, it's raising at only a couple of parts per million, or 1 to 2 per year. But it has to keep increasing. I mean, as long as we're pumping that in, and there's not a very good mechanism to take it out of the air at this point. So that's what we see. This is just a closer up. The carbon dioxide, as I said here, has increased by 100 parts per million, or about 30% since 1960. And of course, plants use carbon dioxide, as I put the notes here, from CO2 to build the plant using the sun's energy. Higher carbon dioxide speeds this up in some crops. Soybeans, wheat, those crops, the C3 crops, some of you have heard that term, they benefit from higher CO2. Corn is so good at taking carbon dioxide out of the air that you can raise carbon dioxide and it doesn't increase. It doesn't help corn photosynthesize very much faster. Now this line is jagged, as you can see. And the reason it's jagged, there's a very good reason why it's jagged. It goes down in the summertime in the northern hemisphere, because there's so much crop and photosynthesis and forest and everything else in northern hemisphere. And then during our winter, it goes back up again. So these drops every year are what the crop is using, or all the plant life, I should say, not just crops. And that includes photosynthetic organisms in the water too. And I think saw somewhere that, the carbon dioxide taken up by microbes and algae and so on, and krill and so on in the ocean is probably greater than the amount that's taken up by land plants, just because there's so much more water surface. Most of this carbon ends up back in the air as carbon dioxide. I mean, people and animals eat corn and respire away that carbon dioxide back, getting the energy from it. So sequestering carbon, a term that you've heard, comes from a more permanent sequestration. I guess putting corn in a bin and leaving it there for 100 years would be sequestering that carbon, but we tend not to do that very much. Wood used to build a house has sequestered some carbon, unless the house burns down. So, we can do that, and soils are considered a place to sequester carbon. And sequestration is a good idea. It's just really difficult to manage billions of tons to help offset some of what we're doing in terms of putting that carbon dioxide into the air. CO2 is not the only greenhouse gas. Water vapor is actually a really important one, but we would be in big trouble without water vapor. So that's highly variable. Evaporation from a water surface does cool the air some, so that's a good thing. Methane from flooded land, swamps, and rice production fields, thawing tundra, ruminants. Yes, the ruminant digestion process produces methane, and escapes of natural gas that's being pumped out of the earth. These all contribute methane, and it's a major source of greenhouse gas. Nitrous oxide, which is mostly released by microbes from nitrogen applied as fertilizer. We estimate generally that at about 1% of the amount of fertilizer N that was applied. And so those three are the additional ones to carbon dioxide. They would make up most of it. Each greenhouse gas is assigned a rating called global warming potential that based on how well it traps heat, but also how long it lasts in the air. So the global warming potential of carbon dioxide is 1 by definition. And for methane, for the 20-year, because they stay in the air longer than a year, the 20-year global warming potential for methane is 84, and for nitrous oxide is 264. So these are not released in as big a quantities or even nearly as big quantities as carbon dioxide, but they have a lot more effect on the warming than carbon dioxide does. So that's why we fret and try to figure out how to reduce the amount of nitrous oxide that's released from cornfields. Well, climate change is not uniformly distributed throughout the world. This isn't a very good picture, but it's how they predict these things. And I just drew a circle here and said, compared to these, this was degrees Fahrenheit per decade. So from 1990 to 2013 was 3 decades. And you can see up here in the Arctic Circle and here in Africa, Asia, or Europe, and out here in the Atlantic Ocean off the eastern seaboard, those have been large increases compared to what we have here in the Corn Belt. And you don't see very much drop, but there's some in the oceans, not much over land. But this tells you, the US Corn Belt has warmed less than many regions in the world. That is expected to continue. And it's a complex thing. The main climate effect is increasing temperature, but that's unevenly distributed. In temperate regions like us in Illinois, this will mean warmer and shorter winters, but may also include more variability in freeze dates. Warming temperatures allow the air to hold more water and increase, but they also increase evaporation. So the dew point is expected to increase, but not necessarily relative humidity. Relative humidity and dew point are related. The dew point is the amount of water in a cubic foot or a quart of air. And the dew point, it measures the amount of water, but the dew point is that temperature at which that water would start to condense out of the air. And so that's not necessarily the same. Because the dew point increases, we would all be more miserable. But if the temperature increases more than the dew point, that means the relative humidity may not increase. Rainfall effects are expected to be less consistent than temperature increases, but rainfall patterns might become more uneven. They already are doing that in some places in the world, with larger storm events and longer dry period. Temperature changes also affect ocean currents and ice sheets. These cause large continental changes like ocean currents slowing down and temperatures change. And also rising ocean levels are pretty much going to happen as the huge amounts of ice particularly in the Greenland. The Arctic ice is going away pretty fast. And so the glaciers in around close to the Arctic Circle are all going to be showing some melting. These changes are going to be gradual and inconsistent, and that's always the case when weather changes over a long period of time. What about weather predictions? Predicting the effect of warming on weather in a region is done by atmospheric scientists using high-powered models that use expected global warming potential carbon dioxide changes. These model predictions vary a lot, so we averaged them. In this exercise we're doing, we're going to use 32 models to give us a best guess. And they make predictions under several scenarios, so we don't know what's going to happen with carbon dioxide and global warming potential for the gases in the air over the next 100 years. So they've modeled these based on, we're using two scenarios here. RPC is what they're called, representative concentration pathway. And RPC 4.5 is what we would consider sort of a medium rate of change that would have global peak temperatures late in the 21st century. And this would mean, this would come about if carbon dioxide emissions would start to decline and start to decline pretty soon. RPC 8.5 is one that will happen if they don't decline. And in fact, if they continue to accelerate like they've been doing. Incidentally, 2020, due to the pandemic, was a considerably lower year. I think I saw it was 7% lower emissions expected for 2020 than for the year before that. So that's a faster rise in temperatures over a longer period, and it's likely if greenhouse gas emission rates remain high. So I'm going to show you this in RPC 4.5 is the medium and RPC 8.5 is the high. So here's what rainfall is predicted to do, and I'm going to move through these pretty quickly. This is, and I said the rainfall is not predicted to change very much, but a little bit. With the RPC 4.5, no trend. RPC 8.5, about 0.6 less by 2075. So very small changes in rainfall. Maximum predicted temperatures, you can see that they're rising pretty consistently here under both scenarios, but much more with the RPC 8.5. 4.5 is about 0.7 of a degree per decade, or 3.9 between 2020 and 2075. And RPC 8.5 is about just double that. The trends are the same across the regions. I did put Central Illinois in here just to keep the number of dots down, but it and Illinois are almost identical. So they're the ones in the middle here. It's going to get warmer. There's not much question about it. Minimum temperatures are showing the similar pattern, and they're going to get warmer as well. And about the same difference, the RPC 4.5 is 0.6 degree per decade, and the RPC 8.5 is 1.2. And as I said, with the other trends are the same across the region, and Illinois is the same as Central Illinois, all of Illinois. Now, we're going to finish up by just showing what we might think yields will do over this same period. One way to predict future yields is just to take current trend lines, and that's what these are. I drew the trend line from 1980 to 2019 right here, and then just extended it out to 2075. And I averaged these over a 5-year period, just so it wasn't an individual one. But over a 5-year period, according to this, the last 5 years, corn averaged 185 and soybeans 54. From 2070 to 2075, this would project a 307 and 86 for the two crops. Do those sound ridiculous? Not really. I mean, we'll see what kind of yields these other models suggest. So here's what the Illinois model that I developed and showed you. This is what it showed. And this is the sausage version, I called it, showing variability over the modeled weather. So these are those 32 models. And for each year, there's 32 yields here as a prediction. Okay, they would use this to say, well, how confident, how confident can we be? But the lines I'm going to show you after this one are just going to be the average of these, sort of the middle 8 models, but it's the same, about the same as the average. And there's where they are. So I put on here the trend line yields, the ones that I showed you, but starting at in 2020, it's 191 for corn, and by 2075, it would be 312. With medium warming or the RPC 4.5, we would increase yields. Well, that one is 2.2 bushels per acre per year, which is what I told you back at the beginning. With the modest warming, medium warming, it's 1.63. It drops to 1.63, which is a considerably slower yield increase, but not an unreasonable one, and gets us to, up to, you can see where it gets us to about 265 or so by 2075. The stronger warming is not as positive as we would guess. And you can see here that's 1.3 bushels per acre per year. And so that gets us up to only about 240 bushels per acre per year by 2075. These are the predictions then. I could do this for each northern, central, and southern Illinois, and they don't look too different. But with that, the temperature increases are the same in the different regions, but they start out higher in southern Illinois, and I think that's why we're seeing less increase there. So they go from 2 bushels of 2.04 to northern 1.8 and central, and about 1.4 in southern Illinois over that period of time. That's with RPC 4.5. And here it is with 8.5, and those are dropped further, 1.8, 1.4 to about 1 bushel per acre per year. So those are pretty substantial decreases. And, they're compared to what we would have if the current trend line just continued. This is then the same thing for soybeans, and they look a little bit less variable, again, on a percentage basis, probably not. And here's the equivalent figure that would have us, we're at today, 2020, we're at 56.2 is our trend line, and the same trend line by 2075 would have us at 88 bushels per acre. And then the warming scenarios would drop that some. RPC 4.5 would get us to 79 bushels by 2075, and 8.5 would get us to 76 bushels by 2075. So those are pretty modest. And here they are by region. So in this case, with soybeans, these regional differences are pretty small. Can we have confidence in this approach? It's not likely to be very accurate in the short term for reasons that include we don't have a way to know how the weather will actually change. Models are just a best guess. Model weather may be more or less tame compared to actual weather, and we can't be sure if or how long yield potentials will continue moving upward at the same rate they've been moving over the past 40 years. Might genetic improvement slow at some point? The bottom line, it makes sense that yields will continue upward for many years, even if the rate of increase begins to slow. And I think that's the part that's, you're going to continue to see projections, if you choose to look, show us yields really declining. And I just think over the next 50 years in Illinois, that's not a very realistic picture. And even if our climate changes, as we've been talking about, I don't think they're going to, be less in the year 2090 than they are today. Thank you for your attention. The 2021 Crop Management Conference unit on how might crop management change as yield change over the next 50 years. We're going to talk about management issues. And so we had to break these up so we could get them both in. Thank you.